Good morning, everyone. I'm Fouad Sakr, a PhD graduate from the Joint Doctorate Program organized by University of Geneva and the Center for Intelligent Sensing at Queen Mary University of London. Today, I'll be presenting a part from my doctoral research titled Tiny Machine Learning Environment Enabling Intelligence on Constrained Devices. In this presentation, I will start by addressing the problem we set out to tackle, emphasizing its significance within our field. Next, I will provide a brief yet compelling introduction and motivation for my research. Following that, I'll present the thesis aim that served as the foundation for my research objectives. And due to time constraint, I will focus on 3 of the 5 main sections of my dissertation, providing insights into the methodologies and results that have shaped my conclusions. And finally, I will conclude this presentation. It's no secret that the number of internet-connected devices has grown tremendously in recent years. Those devices generate massive amounts of data, requiring machine learning and deep learning algorithms for intelligent decision-making. Previously, cloud computing was the only way to support IoT devices due to resource constraints. However, new approaches are emerging that allow more efficient and effective use of IoT devices without relying solely on cloud computing. However, cloud computing's ability to keep up with the growing volume and complexity of data has been outpaced. Also, due to the increase in data breaches and the risk of cloud computing acting as a single point of failure, there has been a paradigm shift towards processing data near its source. This paradigm shift has led to the emergence of tiny machine learning, which enables local cognition and allows smart devices to demonstrate advanced capabilities even when not connected, creating a new Internet of conscious things. However, there are several challenges to the widespread adoption of this computing paradigm, and it's still considered to be in its early stages of development. So let me first introduce you to the field of tiny machine learning. It's a recent computing paradigm that focuses on optimizing machine learning workloads to be processed on constrained devices. In an edge or IoT context, microcontrollers are the typical hardware platform for hosting tiny machine learning applications. These microcontrollers are widely available, cheap, and energy efficient, and often connected to sensors such as microphones, cameras, and so on that constantly collect information about the local environment. Although the majority of edge devices has severe limitations in terms of processing power, available memory, and battery life, the benefits of this shift are significant, particularly in terms of bandwidth, latency, cost, and privacy. To achieve the benefits of tiny machine learning while adhering to the constraints mentioned earlier, we focus on designing and implementing an efficient environment for hosting tiny machine learning applications on constrained devices. So my dissertation contributes to the development of Edge Learning Machine Environment, or ELM. It's an open source platform independent framework that offers 3 primary tiny machine learning services: on-device self-supervised machine learning, shallow machine learning, and binarized neural network on constrained devices. To accomplish this, several optimization techniques were used, including quantization, binarization, memory replacement strategies, and memory filtering. We will explore these techniques in more details later in this presentation. Enabling intelligence on constrained devices can be achieved through various approaches, either in the training phase or in the inference phase. In my dissertation, we addressed both aspects, leading to the development of an environment composed of 5 essential components. Our first service, the Autonomous Edge Pipeline, is designed to empower edge devices with autonomous decision-making capabilities, thereby enabling them to operate independently and efficiently without constant human intervention. In many IoT scenarios, machine learning models are typically trained on high-performance computers and then deployed on edge devices to perform the inference task. However, this approach has 2 significant limitations that affect the accuracy and efficiency of the system. First, statically trained models are not able to adapt to changes in the environment, resulting in reduced accuracy for new samples. And second, supervised learning, which requires a labeled dataset, is not ideal for IoT scenarios where vast amounts of unlabeled data are generated in various domains. To address these challenges, we proposed a novel solution called the Self-Learning Autonomous Edge Learning and Inferencing Pipeline, or simply AEP. AEP is a software system designed for resource-constrained devices, leveraging two complementary approaches: pseudo-label generation with a confidence measure and periodic on-device training. The AEP is a non-device iterative pipeline that alternates between clustering, training, and classification. The pipeline starts with the periodic k-means clustering of the input data, which yields pseudo-labels for each sample. The labeling results are then evaluated by a confidence algorithm that determines the level of confidence in each decision. This step is crucial for preventing noise and outliers from impacting the training process. Once the important samples are selected, the training process is performed using one of the two supported algorithms, decision tree or k-nearest neighbor. The resulting classifier is continuously updated and used to classify the incoming samples. Developing the AEP posed several challenges that required innovative solutions. First, we needed to determine the level of confidence in each clustering decision made by the k-means algorithm. To address this challenge, we implemented a confidence measure based on the soft k-means algorithm, which calculates a weights for each sample that determines its degree of membership in each cluster. Second, the target devices have limited memory, making it critical to manage the amount of data to prevent memory overflow. To manage this challenge, we implemented three memory management algorithms: first in, first out, random memory filtering, and confident memory filtering. The latter algorithm prioritizes samples with higher confidence value, ensuring that only the most important data is retained in memory. Finally, we could not find a publicly available version of the decision tree training algorithm for Cortex-M microcontrollers, so we implemented the decision tree algorithm from scratch in plain C, which required careful optimization and testing to ensure its performance and reliability. The AEP process flow diagram illustrates the interaction between k-means clustering that generates pseudo-labeled data, which is used to train either the decision tree classifier AutoDT or the k-nearest neighbor classifier AutoKNN. The diagram also includes memory management to prevent overflow. To begin, the memory is filled with data sample up to a user-specified initial threshold. When the initial threshold is reached, k-means clustering is executed on the collected samples to obtain their pseudo-labels. If the user selects the AutoDT option, the decision tree training algorithm is executed. Alternatively, if AutoKNN is chosen, the k-nearest neighbor classifier is used. Once the trained model is ready, the AEP starts classifying subsequent samples. To improve classifier performance, new samples can be stored in the new sample memory section until the update threshold is reached. Then all samples are moved to the memory and k-means clustering is run again, providing the new set of pseudo-labels and updating the classifier. If the memory is full, one of the three data filtering algorithms, FIFO, random, or conf memory filtering, is run to prevent memory overflow. We conducted experiments on two datasets, one from the industry, CCOM, and another from healthcare, Pima Indian diabetes, using the H7 microcontroller. We aimed to answer four research questions through these experiments. First, we examined the system's robustness by evaluating the AEP with and without the confidence feature of the soft k-means algorithm. We found that including the confidence feature leads to a performance increase in both datasets. Second, we investigated the possible advantage of memory management algorithms, and our results showed that the conf strategy has a slight superiority over the other two memory management algorithms. In the third research question, we analyzed the timing performance of each component of the AEP on the H7 microcontroller. While we evaluated the performance of each component, for the sake of time, I'm only presenting the classification latency. Overall, the latency time is relatively low in all cases. However, the periodic clustering and training introduce some overhead after each system update. To address this, we provide a one-shot implementation within the AEP that performs clustering and training only once when the maximum memory size is reached, without any further update of the classifier. This implementation results in a slight decrease in accuracy but avoids the overhead caused by periodic clustering and training. And as a final experiment, we compared the performance of AEP with baseline models trained in the cloud in a fully supervised scenarios and then deployed on the H7 microcontroller. From the results, we can see that the AEP achieves comparable performance to the baseline models. Now let's move on to the next part of this presentation, which is the Edge Learning Machine Framework. In this work, we aim to address the lack of quantitative analysis on the performance of common machine learning algorithms on edge devices, such as ARM microcontrollers, which limits the development of new applications and the upgrading of existing ones through edge computing. Thus, the second service we developed for constrained devices is the Edge Learning Machine Framework. This platform-independent C language framework allows for training on desktop or laptop computers and performs inferences on microcontrollers. It includes 3 supervised machine learning algorithms, support vector machine, k-nearest neighbor, and decision tree, and leverages the STM-X-Cube-AI expansion package to implement artificial neural networks on STM32 Nucleo boards. The Edge Learning Machine Framework has undergone rigorous testing with various algorithms, configurations, hardware platforms, and datasets. The proposed Edge Learning Machine Framework is composed of 2 modules. First, the DeskLM module, implemented in Python and acts as a wrapper for various machine learning and deep learning training frameworks, such as Keras, Scikit-learn, and TensorFlow. This module is used for training and testing on a PC, where it identifies the best models by hyperparameter tuning for an input dataset. The process involves specifying the dataset, the range of parameters to be examined, the pre-processing techniques to be used, and more. Once the best model is generated, it's ready to be transferred to the embedded device. Secondly, the microLM module reads and executes the models generated by the DeskLM module. If the model is artificial neural networks, X-Cube-AI extension package from STMicroelectronics is used to perform the inference. Otherwise, MicroLM provides the C implementation for the other supported algorithms, whether it's a classification or a regression problem. Notably, MicroLM can run on both microcontrollers and desktops, making it a versatile module. During our analysis, we aimed to answer several research questions covering topics such as inference performance, training time, pre-processing, and hyperparameter tuning. To perform this analysis, we used 6 ARM Cortex-M microcontrollers from various families and series, ranging from less powerful to the most powerful. We also evaluated our framework on 6 benchmark datasets that are representative of the IoT field. To summarize our extensive analysis, we were able to achieve the best performance on all tested devices with at least one algorithm compared to a desktop machine. We cannot present all 32 tables, but this table provides an overview of our results. For instance, both SVM and ANN achieved the highest performance of 84% on the hard dataset, with an inference time of around 1 millisecond on the STM32F4 microcontroller. The optimal configuration for these algorithms are listed in the last column. The final component of my dissertation was the CBIN neural network inference engine. Unlike most deployment solutions that are designed for 8-bit quantized networks, our work concentrates on creating an inference engine dedicated to binarize the neural networks. Quantization is a popular tiny machine learning technique that reduces the number of bits required to represent weights and activations. However, we concentrate on the extreme form of this technique, which is binarization, where parameters are represented using binary values. This approach achieves significant benefits on the edge, including up to 32 times storage savings and up to 58 times faster inference. Given these advantages, we developed an inference library for binarized neural networks that can run on resource-constrained devices, namely CBIN neural network. The library is written in plain C language and designed for easy use on any edge device with particular emphasis on memory usage. To maximize the memory savings from binarization, we used bit packing to save weights and activations. As you know, in C language, the smallest data type is 1 byte, which would negate the memory savings of binarization. So to overcome this issue, we encoded -1 as 0 and packed the weights over the channels to a multiple of 32. However, if the number of channels is not a multiple of 32, we padded them to achieve optimal memory access patterns. This animation shows how the weights are packed. We have implemented a set of operators to enable binary convolution neural networks inference on resource-constrained devices. As time is limited for this presentation, I will focus my explanation on only one of the operators, specifically the binary input binary kernel convolution, or BBConv2D for short. The BBConv2D operator is designed to handle bit-packed weights and inputs, producing a bit-packed output. By leveraging the pop count and XNOR operations, the convolution computation can be optimized as a binary matrix multiplication, resulting in significant performance gains. In our pursuit to improve the accuracy of binarized neural networks, we utilized various optimization techniques. Firstly, we employed the binary optimizer to enhance the performance of BNNs. We also found that introducing an unbalanced distribution of activations through the use of the Pirilu activation function after each convolutional layer can lead to an increase in accuracy. Furthermore, we implemented several latency optimization techniques to increase inference speed and improve operator performance. To achieve this, we performed layer fusion for batch normalization and Pirilu layers to minimize redundant reads and writes. Additionally, we applied loop unrolling and enabled memory caching. This part of my thesis involved a workflow that includes the following steps. We begin by utilizing the LARC framework, an open-source Python library for training neural networks with low precision weights and activations. This framework is used to model and train the networks required for our analysis. Once the network has been trained, we extract the network parameters and convert them into a compatible format for the inference phase using Python. Additionally, a main function is generated through this script, which will be executed during inference on the device. Finally, we utilize the main function, network parameters, and operators from the Sieben neural network inference library to perform inference on constrained devices. This enables the implementation of binarized neural networks on devices with limited resources. To evaluate the performance of the proposed inference engine, we conducted two case studies. In the first case study, we selected robotic touch modality classification as our use case, which has been previously addressed in machine learning literature. The dataset consists of three modalities: sliding a finger, brushing with a paintbrush, and rolling a washer. To optimize the dataset, we conducted subsampling and data augmentation. This slide displays the architecture that we designed for our first case study. For testing the proposed library, the model was implemented on the H7 microcontroller. Our model achieved a higher classification accuracy of 78.84% compared to existing solutions targeting the same touch modality classification problem. Also, in terms of model size, our architecture requires 2.3 kilobyte and achieves a 15% improvement compared to the only BNN presented in the comparison table, despite having a larger architecture. This improvement can be attributed to the efficient 32-bit packing of weights, while the HCNN accelerator was designed with a 16-bit fixed point representation. Although a direct comparison of latency between models implemented on different hardware platforms is not straightforward, our proposed library was able to speed up the inference process and meet real-time constraints with an inference time of only 0.6 milliseconds. To demonstrate the versatility of the Sieben neural network inference engine and other tiny machine learning domains, we selected a computer vision application represented by the CFAR10 dataset. This dataset comprises 60,000 RGB images of size 32 by 32 divided into 10 classes. For this case study, we used the small CFAR architecture as a reference architecture. This is a small network that is commonly used in the tiny machine learning field for the CFAR10 dataset. Our experimental analysis on the STM32F7 microcontroller demonstrated that our library outperforms existing state-of-the-art tiny machine learning deployment solutions. Specifically, Sieben neural network speeds up inference by 3.6 times and reduces the memory required to store model weights and activations by 7.5 times and 28 times respectively. However, there's a slight 2.5% drop in accuracy. It's worth mentioning that our library allowed us to fit the same model on extremely constrained devices, such as the STM32F0, due to the significant memory reduction achieved. To conclude this presentation, we have introduced a comprehensive suite of frameworks and solutions for hosting tiny machine learning applications on constrained devices. These frameworks include the Autonomous Edge Pipeline for on-device training using unlabeled data, desk-LM, and micro-LM for model training and inference, and also the Sequent Neural Network Inference Engine, which allows for the efficient execution of binarized neural networks on constrained devices. Our experimental results showed that our proposed solutions outperform state-of-the-art tiny machine learning deployment solutions with significant improvement in memory requirements, inference speed, and accuracy. This slide highlights that all the presented work has been made available on an open source basis within the ELM environment. Looking towards the future, we aim to continue improving and optimizing our environment with a particular focus on the Sequent Neural Network Inference Engine. Some potential avenues for improvements include adding support for single instruction multiple data or SIMD for some of the available operators to further improve performance, developing a dedicated optimizer for binarized neural networks to mitigate the performance degradation caused by binarization, exploring constrained neural architecture search as a potential solution for finding the best architecture while considering the constraints that allow for porting these networks to embedded devices. In addition, we plan to investigate the possibility of running transformer networks on tiny devices, particularly for computer vision tasks, by leveraging available optimization techniques. And that brings us to the end. I would like to thank you for your time, and if you have any questions, please feel free to ask, and I will do my best to answer.